Hello and welcome to Scintillator Physics Basics. In this module, we are going to talk about the types of radiation, scintillation detectors that can detect radiation, how to interpret the results of detection, and finally, we will take a deep dive into how different kinds of radiation interact with matter. There are many ways that we are exposed to radiation in everyday life, from light to microwaves to cell phones. However, most of these kinds of radiation are non-ionizing. This means that they have very low energy and do not interact with matter, which makes them harmless. At the other end of the spectrum is ionizing radiation. This refers to things like gamma and X-rays. These kinds of radiation have very high energy and can interact with matter by knocking electrons free from their atoms. This interaction can be dangerous to people who are exposed to it. There are a few kinds of ionizing radiation. First up, and most important, are the kinds with high penetration properties that can travel far from the source of the radiation. Gamma and X-rays fall into this group. These are photons or particles of light instead of matter. Because of this, gamma and X-rays are only shielded by a very dense material such as lead. The other kind of high penetration radiation is neutron radiation. This is just a single neutron, a subatomic particle with no electric charge. It can be stopped by materials with a low atomic number, so shielding for neutron radiation is usually hydrogen-based, for example, water. The other kinds of ionizing radiation is low penetration. These are less important for radiation detection because the radioactive particles don't often travel far from their source. Alpha radiation is very stable and can be stopped by a person's skin. Beta radiation is a bit more penetrative, but a thin layer of plastic is enough to stop it. So why do we need to detect radiation? For several reasons. Radiation detectors are valuable tools for major industries around the world. X-ray, PET and SPECT scanners are vital parts of the medical industry. Detectors are also used in oil and gas industries to help locate new wells to drill. And radiation detectors are an important part of national security, used at borders and airports to protect people around the world. Let's focus in on the security market. Radiation detectors are commonplace at many ports, airports, and border crossings around the world. These detectors are used to scan for dangerous materials entering these countries. Different kinds of detectors are needed for each application. Large portal monitors allow vehicles to move through quickly, while smaller handheld detectors can be used to determine how much radiation is present and what is causing it. Let's have a look at that handheld device. This is a RID. That's shorthand for radioisotope identification device. This detector can identify not just the presence of radiation, but also tell what the radioactive material is. Let's have a look at how it works. This is the basic makeup of a scintillation detector. The specifics of detectors will vary, but these parts are necessary in every detector. First, let's look at the most important part of the detector, the scintillator. So what is a scintillator? Well, this is a piece of crystal or plastic that has an interesting property. When exposed to ionizing radiation, it gives off light. These scintillators come in many different sizes and can be made of many different materials such as sodium iodide, lanthanum bromide, and many more. Now let's look at the next step in the detection process. After the scintillator gives off light, the next step is in the photodetector. A photodetector's purpose in a detector is to detect light from the scintillator and turn it into an electrical signal. There are two main kinds of photodetectors. The first is a photomultiplier tube or PMT. This detects the light and releases an electron into the glass tube. The electron bounces between diodes in the tube, each time causing more electrons to release, turning from 1 into millions. By the end of the tube, the electrons form an electrical signal that is sent along the detector. PMTs are reliable and accurate, but are heavy, fragile, and power-intensive. The other kind of photodetector is the silicon photomultiplier or SiPM. This is a relatively new technology but works on similar principles to a PMT, turning the light from the scintillator into an electrical signal. The advantage of the SiPM is that it is much smaller and requires less power, making the detectors much more mobile and versatile. However, it is a technology that is still being developed. Once the electrical signal is sent from the photodetector, the scintillation detector has to display this information somehow. Let's take a look at how these detections are displayed. This is the photoelectric spectrum, a graph of all the readings made during a detection. The spectrum can be divided into two separate regions. On the lower energy, left side of the spectrum, are the partial detections. These detections are not fully accurate since they don't represent the full energy of the radiation. The peak on the higher energy, right side of the spectrum, is called the photopeak. This peak represents the full energy of the radioactive source. Because of several factors, the photoelectric spectrum often contains small inaccuracies that can distort the spectrum. To describe the accuracy of a photoelectric spectrum, we use a measurement called energy resolution. What is energy resolution? It's pretty simple. Energy resolution, also called pulse height resolution, is a percentage value used to describe how precise a photoelectric spectrum is. The taller and thinner the photopeak, the smaller the percentage. The smaller the percentage, the more precise the spectrum. There are a few different factors that impact energy resolution, including the temperature of the environment and the material and age of the scintillator. For example, sodium iodide has an energy resolution of 6.5%, and lanthanum bromide has a much better energy resolution of 2.2%. Energy resolution is measured in percentage. But what do those numbers mean? Well, it's the ratio of the width of the peak to its height. For the width, we use the width of the peak at half of its max height, also known as the full width at half max, or FWHM. As the width decreases or height increases, the energy resolution will decrease, representing a more precise photopeak. But all of this leads to the question, why is energy resolution so important? Well, most radioactive sources give off a specific energy. So if we know the energy, we can determine the source. Smaller energy resolution means that we can be certain of the energy of the radiation. It also means that the peak will be taller and thinner, raising it out of any background noise and away from partial detections. Energy resolution can also be used to track the age and degradation of a scintillator. Energy resolution is one of the most important properties of a scintillator. What are the errors in the spectrum that make it inaccurate? Well, they occur throughout the detection process. When the scintillator interacts with radiation, it can create the wrong amount of light. This is called non-proportionality. Then the photodetector can detect the wrong amount of light from the scintillator. This is called transfer non-uniformity. And then the photodetector can send the wrong amount of electrical signal to the display. This is called noise. All of these lead to a photoelectric spectrum that is inaccurate. Now let's go a level deeper. What exactly happens inside a scintillator when it gets hit by radiation? Well, when any gamma or X-ray interacts with matter, two interactions are likely to occur: the photoelectric effect and Compton scattering. First, let's have a look at the photoelectric effect. This occurs when the photon hits a tightly bound inner shell electron. The electron absorbs all of the energy of the radiation and is ejected. These interactions make up the photopeak. The probability of the photoelectric effect can be explained by this formula, where Pe stands for the photoelectric effect, Rho stands for the density of the material, Z is the atomic number of the material, and E is the energy of the incident radiation. Higher Z means a denser material, which together mean that the photoelectric effect is more likely. Hence, higher Z materials make better scintillators. Now let's have a look at Compton scattering. In this interaction, the radioactive photon collides with a loosely bound outer shell electron. This photon then scatters off the electron, only giving some of its energy. Because only a portion of the radiation energy is transferred, this interaction makes up the low energy portion of the spectrum. The likelihood of this interaction can be explained by this formula, where Cs stands for Compton scattering, Rho stands for the density of the material, and E stands for the energy of the radiation. When we compare the probabilities of these two interactions, the relationship between the two becomes clear. As energy increases, the likelihood of the photoelectric effect decreases much more quickly than Compton scattering, meaning that Compton scattering becomes much more likely at higher energies of radiation. Now let's talk about neutron radiation. This is a bit different because neutrons don't directly ionize matter or interact with electrons. Instead, neutrons interact with the nucleus. There are two kinds of neutron interactions. The first kind of interaction is called a scatter. The neutron scatters off the nucleus, giving it some kinetic energy and sometimes causing it to emit a gamma ray. This kind of interaction can cause ionization, but it's not certain. The other kind of interaction is called absorption. In this interaction, the neutron is absorbed by the nucleus, which becomes excited and unstable, eventually fragmenting into several smaller pieces. This kind of interaction always causes ionization. The probability of each interaction will vary from detector to detector. This brings us to the end of the module. In summary, we began with the types of radiation, explaining ionizing radiation, and then going into the applications of radiation detectors. Then, we broke down how scintillation detectors work, following the detection process from the scintillator to photodetector to the display. Next, we talked about how the accuracy of a detection can be measured and how inaccuracies occur. Finally, we went into the ways the different kinds of radiation interact with matter in different ways. Thank you for watching Scintillator Physics Basics. We hope you enjoyed the video and learned something new. See you in the next module.